Hi, everyone. Thank you for sticking around. Let's get to it. So, some of you might have noticed in the past years, particularly since 2013, the influx of Android security issues, particularly talking about lower level security, so kernel exploits like roots, bootloader unlocks, and so on. And on the slide, you just see some random sampling of various exploits that have been published. These are all from 2013. And the main thing to notice is that these things come from all kinds of places. You see XDA developers forum posts, random tweets, sometimes full disclosure, sometimes coordinated straight to the vendor, sometimes heavily obfuscated exploits that essentially advertise a feature but don't want to tell you how they managed to do that. And so this presents a number of challenges for the vendor side to want to respond to these things. There are, like I said, a number of places these can come from, literally different languages. I mean, spoken languages. On the top corner, you see that was a kernel 0 day, just some random Chinese tweet, and it's a full-on privilege escalation exploit hidden inside the binary that's tweeted there. And one of the things that makes this more challenging is the mobile ecosystem, particularly the Android ecosystem, is quite a complicated beast. Starting with the chipset vendors, which is what Qualcomm is. For those of you not familiar, we're the largest fabless chip maker in the world. The tagline for the products is at the heart of devices you love. Long story short, if you have a smartphone, it's probably a Snapdragon, or it has one of our processors in it. But we're not the only system integrators in this space. You have the device manufacturers, and then you have your network operators. So when it comes to the attribution of whose problem would some published root be, it's usually not very clear. So like I mentioned, this affects a number of different players, and this presentation is basically about the perspective of Qualcomm about Android incident security response. So just as we get started, a couple of words about our team that are working. So basically, in order to be able to handle the volume and the complexities of these kinds of hacks, we have a dedicated team with essentially 3 times of responsibilities. We do attack intelligence. The idea is to monitor the public research and to understand the attack surface as it exists in the actual field commercial devices in order to then be able to be responsive, pick up published exploits or hacks, and do a root cause analysis of them, figure out what the problem is, obviously with the final goal being patching out issues that are found. And then the third part is to feed all of that back to a secure development lifecycle through gap analysis and figuring out well what the roots I suppose tell us about what areas are really worth further hardening. And that last sentence takes us to the state of Android kernel security as it was in 2013. So on this graph, you see what you see here is the list of the all the Android security incidents from Qualcomm's perspective, which means all the bugs that you would attribute to specifically the Qualcomm Innovation Center, which is a subsidiary of Qualcomm that handles the Android work. The main thing, apart from all the dots, is that you just want to take away is that in 2011 there was a single exploit. 2012 there were 3, and then in 2013 you see the numbers much larger. This picture just shows 2013, and this basically this alone tells you that clearly there were things that we needed to do to kind of stem the tide of this kind of explosion of issues. And so that's one of the takeaways. And the other takeaway is if you look behind what these various exploits actually were, obviously not taking away from the researchers who found them, and many of them are friends of the show, but most of these exploits weren't very sophisticated because they didn't need to be. So you're not talking about fancy exploit mitigation bypasses. You're not talking about ROP and whatever new techniques to get around some hardening measures. You're instead talking about bugs like, oh, there was an mmap interface left open that allows user space to just map kernel memory straight up and do whatever you want. Obviously, kudos to those who found these, but it gives you an idea of the level of difficulty associated at the time with finding and exploiting bugs for privilege escalation in Android, in our case in particular. And so that gets us to what it is that we wanted to do, which is just kind of showed on this simplified graph. Essentially, the idea is that if you compare what exploits or incidents basically cost to the defense or the offense, for the defense, the cost is basically mostly influenced by factors like if the attribution is unclear, that just translates to more work for you until you find out whether you have to worry about something or not. If you don't have good analysis tools, then you're going to have a hard time getting through obfuscated exploits to figure out what the actual problem is. And if you don't have a solid process to actually push patches through the system, then even if you're figuring out what the problems are, even if you're coming up with a good fix, those problems are going to linger around for a very long time. Whereas on the offense side, if the general code quality is just not very good, it costs less to find bugs. If there are no hardening measures, it costs less to turn POCs to actual exploits. And if the zero-day windows are long, like I was talking about the patching process, then your exploit, however you want to monetize that, is just more valuable. And that's the same for whether you just want to put it out there so that people can use it, or if you're trying to sell it in any way. The longer that bug stays undead, the better your return is. And essentially what we felt was that we were more up in that corner, and we wanted to get down Android kernel, state of security more down into this area. So for basically the meat for the rest of the presentation, I'm going to talk about the various aspects of that work, of how we get from the X to the check mark, if you will. So the first thing that I'm going to mention is an internal bug finding exercise that we did. Essentially, recognizing the increase in numbers, we just said, okay, you kind of want to put things to the side and just focus on this area. Of course, a one-time manual auditing campaign or a one-time campaign is not going to get rid of all the bugs ever, clearly, but it can significantly change the dynamic for how shallow the bugs are essentially in your code base. So to give you an idea of the effort, this was something like 11 engineers with varying degrees of expertise in kernel security. And it was about a 2-month effort altogether to look at the code, use various things, manual auditing, fuzzing, static analysis. So what makes this difficult is, all right, let's go look at all the Qualcomm code in the kernel. Okay, where is it? So to give you an idea of this, of course, probably everybody knows this if you're familiar with Android platform, that at the heart of it, it is just Linux. It's based on a Linux kernel. So you would think that, that's all just upstream. But the reality is that there's a lot of code that ends up being added in specific to the platform. And these are mostly, obviously, drivers for the specifics of the hardware platform, audio drivers, video drivers, GPU drivers, and so on and so on. And another thing to see is that the way these things are released in the Android space is there's an upstream kernel, and then this is incorporated and fine-tuned for our processors by Quick, and then published as open source on something called the Code Aurora forum, and that's where everybody takes them from. So essentially, when you think about your Sony or Samsung or Motorola, just to give some examples, Android devices, then the ownership of that kernel comes through upstream, goes through Qualcomm, and then will go to the device manufacturer. So that also makes us responsible, long story short, for, in a way, for all of the kernel in terms of the release management. And this here is just a tree map that kind of gives you an idea of how much code we're talking about. Altogether, it's about 12 million lines of code, and the red is the part that is either written entirely by Quick or has commits in it by Quick, so authored by us in part. So clearly, the whole point is that it's a non-trivial amount of code. So something like, let's take 24 guys and go through all it, and from now on there's no bugs, that's just a non-starter. Especially with it being a moving target. That's why, again, the goal was more to get rid of some bugs. And again, the theory was that, well, there's probably a lot of shallow bugs, and doing a campaign like this gives you an idea of truly, what this attack surface looked like. So to get to the punch right away, this is the results. So altogether, 260 zero days were found in this effort. Very large number of them are information leaks. This is basically this is a classic Linux problem that, or classic software security mistake you can make in writing Linux kernel driver code, that if you're passing some structure back to user space as a return from an ioctl call, for example, and you're not taking care of properly initializing all the members of that structure before you copy it back, then you're going to essentially send back remnant bytes from inside the kernel memory to user space. And these types of leaks with carefully crafted inputs can be used to essentially read out secrets such as stack cookies from the kernel space that user space shouldn't have access to. So that contributed to most of the medium issues, and then buffer overflows, null dereferences, and just straight up array index validation type of issues, these are things that can lead to arbitrary reads and arbitrary writes, which are really the most powerful kind that you can think of when it comes to memory corruption type of issues. So these type of buffer overflows and index problems were the bulk of the 93 high and then the 3 critical issues. So obviously, that's a large number altogether. So that was our biggest takeaway, that just doing this manually all the time doesn't scale. So you need to find some alternative ways to continue to make sure that as you have more code churn and you have more edit code, these types of shallow bugs are weeded out earlier on in the process. So that was a big takeaway for us. Another one is that we realized that we used to carry lots of that code. So if you go and look at earlier releases from, like I mentioned, Code Aurora, then you're going to see all this source code, and a lot of it is basically going to be not compiled in and not really used. But because of the open source nature of all of this, really you don't have perfect control over that. And when I say that that's not compiled in, that's what you think, right? But that might not necessarily be the case. So the point is, you're responsible even for the code that you think is not compiled in. So a lot of the bug fixing in this sense actually ended up being just completely swiping out code that shouldn't be there at all. And like I said, the next step that showed from this clearly is that we need to scale So you use some automation apart from manual testing. So now I'm going to talk a little bit about this part, specifically the work we have done with static analyzer and fuzzer tools to find bugs in Android, in the Android kernel space. So first, a little primer to give an idea of the challenge of doing something automatically versus manually. So this is just an example ioctl driver code snippet with a bug that's essentially obvious if you're or trivial really if you're familiar with this kind of code. What you want to see is that the third argument passed into this ioctl call, the arg, that comes from user space, and then the copy from user calls are the Linux kernel APIs to securely transfer memory from the user space to the kernel space so that the kernel can go and actually parse those arguments and so on. And so this is a very, very typical issue. You copy in that argument, which is used as a size, and then you do another copy using the size you just copied in from user space to copy in one more. And clearly, you're not checking the size. So on the second copy from user, it's easy to overflow that data buffer, which is now in kernel space. So boom, straight up kernel memory corruption. So again, this is trivial to find. If you've gotten through the problems of like, well, now I'm looking at this, what is that? 20 lines of code. Like I mentioned, you first had to find these 20 out of the 12 million, but once you're there, it's easy to find. But automating it is a little bit harder, especially because these kind of things like, and we know that that's what a copy from user does, and we know that this is the one that's actually an ioctl call. Notice, for example, that this is original real code, right? This is not like a toy example. Notice how the arg is not annotated with underscore user, right? So nothing here tells you that that comes from user space apart from your domain knowledge, where you know that that happens to come from user space in this code snippet. So the first thing we looked at was you can formulate these queries in your head almost really just in spoken language, where you say, show me bugs where you have a copy from user, where you copy in an argument that's the size, it doesn't get checked, and then it directly gets used in a next copy from user, and it's the size for that call. And there are typical kind of problems like this in the kernel space. Again, it's at a level abstraction more above than just find me a buffer overflow, but you're specifying it to things that are unique to that domain. And so we looked at a way to do this, to define queries like this, and use a static analyzer that will automate that kind of search for us. And this is where a tool called Yorn enters the picture from a researcher called Fabian Yamaguchi. To give away the thing, the takeaway is this is, especially if you're like a security researcher, you're thinking more in limited term engagements for looking for bugs. This is an awesome tool. So I very highly recommend to make it part of your arsenal for this kind of work. So what is it that Yorn does? It's essentially has a parser in it that takes the source code and generates various kinds of graphs that are actually typical in automated code analysis. And then where it becomes powerful is it combines those graphs into a unified view that helps you using a query language that's called Gremlin. You can think about it like if it's SQL, but it has its own syntax and different. And it allows you to define queries that are going to be very close to what you would just say, like I mentioned, the double copy from user case. For some background, the types of graphs that this uses include basically three things. There's the abstract syntax tree that's typically used, of course, inside compilers as well. This is essentially a laxer step of abstracting away the syntax of the language and taking care of nesting and so on. It basically lets you traverse the code in a useful way or in an automated fashion. And then your control flow graphs, this is a prerequisite to be able to follow the transfer or the transfer flow, so it gives you an idea of how you would get from one piece of the code to the other. And then finally, the program dependence graph is something that allows you to look at reachability and look at tainting. And that's what I talk about there is the ability to say something like, show me a case where this variable flows to that variable, and during that path it's not changed or it's not restricted, that kind of thing. And so we used this and came up with queries on our own. What you see on the slide is an explicit query that you could just feed into Gremlin. I think the main takeaway is, at first this looks a little bit like, wait, what's there? You're not necessarily familiar with the syntax of it. Like I said, it's not SQL, it's not Python, whatever, so it has its sort of own syntax. Our experience is there's some ramp-up time to learn actually how to use this. But once you got it, it's actually pretty useful, and it becomes more straightforward to turn your ideas into actual queries. To give an idea of the kind of things that we looked for, so we created queries for things like there's no access OK type of check when a variable from user space gets dereferenced, the information leaks coming out of uninitialized structures being passed back, typical memory corruption cases coming from situations like I mentioned before. So essentially, you look for a path where you know that a length type value is passed in and it's not restricted before it gets used. And then some other things that are unique to Linux, I suppose. So for example, if you're not familiar, when the heap allocator inside Linux, like kmalloc, if you pass 0 to it as a size, then what you're going to get back is a valid pointer, but it has a specific value. So it's not a null pointer. It's the value of the simple 0 size pointer, which happens to be 8, I think. The bottom line is if you allow 0 size kmallocs to happen because you allow a value that comes from user space to directly be used as the length value without checking that it's not 0, and then on your kmalloc return check, you would do the typical of it didn't fail, so it's not null. But if you forget to also check for 0 size pointer, then you're going to have a memory corruption problem because you think that you got something useful back, but it's not actually valid to go right there. Another thing that I mentioned earlier is open mmap interfaces that allow mapping of kernel space memory, and then things like debugfs or sysfs or procfs files being created with 2 permissions, so like 666 permissions that, again, straight up allow you to access memory that you shouldn't. Altogether, we spent about 4 weeks to coming up with the queries and making them work. Created 9 different checkers, and with like a 30% true positive rate, found 100 O days this way. So I think that's pretty good return. So my takeaway is it's a useful tool to consider. And just to make that point clear, one of really the strong points of Urine is that its parser is fuzzy and very good at being able to parse code that is not complete or may not compile perfectly. This is something that I've seen with some commercial static analyzers, that's kind of a painful step to get to the point where this is even able to properly parse the code so that it goes and does stuff. And Urine in this area does really, really well. It will kind of nicely glance over the parts and still give you a bang for your buck. And I mentioned before, next to static analysis, fuzzing as well. So that was another area that we looked at. One thing that was an obvious choice for us is to look at Trinity, which is a kernel of the ioctl or system called Fuzzer developed for Linux, and this is you can say it's a de facto standard tool. So upstream Linux, this gets used and finds bugs. However, it didn't support Android. It didn't support ARM. So we did that work on our own. So we created our own port of Trinity to make it useful for Android, and then use this specifically focusing on ioctl calls. Again, just from going by our experience, that's where we see most of the issues. Obviously, the complete range of system calls in Linux is more in the 100 plus, right? So there's all kinds, but we focused on ioctls specifically. And then so what we did is a porting effort to just make this thing compile and run on Android, defining models for our own kernel drivers so that it can fuzz them. And we added some useful, just convenient stuff like crashing or like binning crashes so that you recognize when some bug is something you have already hit, or creating very simple reproducers so that essentially whenever we had a crash, what came out of it is 7 lines of valid C. That is, here you go, it compiles as your POC. You can go give this to the say product team that handles this and say, here's the bug, this is the bug. You can go run this, and you get the crash. So this tool, again, during our testing, fared pretty well. Just in the couple months' time of coming up with this, it found us something in the order of 20 plus O days. And since then, this has become a standard tool at Qualcomm. So the Quick team uses this in production, fuzzing all the driver code that gets written. And then in-house, we over time also added some more intelligence to it. So the input that it generates is more grammar-based, and it's more of a smart fuzzer than a dumb fuzzer, if you will, as it before. So when it comes to lessons, I've talked to you now about all the cool stuff, like, hey, it worked, and we found all these bugs, and how great is that? And I think if you are like a pen tester and you want to look into the area of look into this area and look for bugs, then I think these are pretty good tools to think about. But if you're on the other side of it, so you don't just have to find the bugs, but also fix them, in particular, then there's going to be a difference between what works for a security guy and what works well in production. There's all kinds of scaling issues associated with this stuff. So what I told you about Urine is great, but the tool doesn't have the types of intelligence that like really robust, mature, professional static analyzers have, that give you scale, that give you lots of nodes and coordination with them, that give you a good reporting, which is consumable and actionable more than the text file output of Urine, which is useful for me or us, but not so useful when you tell your 3,000 kernel developers, now go use this. The output is a bit of a text file, but hey, so that doesn't work too well. So I guess for more of a on the vendor side, or if you want to do something like this on a long call, my advice would be these type of tools, like Urine, will get you to a point where you get a good early feedback on how bad your code is here much quicker. So they are worth checking out. And then if you decide that, oh yeah, this is an area where we definitely need a good static analyzer, you probably want to look for something that will also handle the challenges with scale. Excuse me, with scaling. So moving on from talking about finding bugs in various ways, I mentioned in the beginning that whether you have ODAs or unfixed bugs is one thing, but how hard it is to actually turn them into something other than a crash is the second part of the story. So now I'm going to talk a little bit about what we do in this area. This is the one slide essentially where I mentioned userland, where we also did various hardening at Quick. A big thing is these are things you would think of that vendors should be doing, and I suppose we do. So getting the privilege levels of various things like daemons down to the minimum, making sure that driver nodes that are exposed are not overexposed. Again, if you go back a couple of years, this was an issue with a lot of the drivers, that everything was 666, and drivers that unprivileged shell users should not have access to at all. In particular, on Android, you have all the Java layer stuff, right? You have all the APIs that apps are supposed to be using. So this kind of use case of let me directly use the raw ioctls, really, for the most part, shouldn't be what unprivileged things are on the system are doing. But, as they say, Android privilege model is just Unix, right? So if something is 666, then by default, your app is just going to be able to access it. Doesn't matter about what permission it has in its XML and all of that stuff. And then, of course, SE Linux has really come along on Android as well. So we do a bunch of work on defining policies and making use of that. Like I said, most of this userland stuff is a little bit outside the scope of driver interfaces and what's inside the kernel and that type and privilege escalation from that vector. But I wanted to mention it because a lot of people work a bunch on that as well. So yeah, credit to Quick for that work, I suppose. And then on the kernel side of things, we obviously try and follow the upstream development quite closely. Sometimes that means you get the benefit of patches. Sometimes that means you more get the benefit of ideas. A lot in some cases, Linux kernel hardening implementations first are patches that only exist for like x86 or 64. So if you want to make use of it on ARM, you have to do some extra work. And then there are also things specific to an embedded environment like this, I suppose. And so next I'm going to talk about some of the things that we did here that are available in the Qualcomm authored like MSM kernels today. So a big thing is early randomness. This has gotten a lot more notice this year. Basically, the idea is that there are things inside a kernel that for security will require good source of entropy. Whether you're talking about your stack cookies, or you're talking about randomizing vector page content, you're talking about ASLR in a kernel context. For these things, you need good entropy. If you don't have good entropy, it's basically not going to be as good as you think. Specifically, if you're not familiar, I would highly recommend to check out Tarjay Mons, I hope I pronounced that name right, work that he did on iOS where he showed that essentially this kind of problem existed, that the RNG was not robust enough, so you were able to get back its state and just the whole thing just unfolds because you just derive back, okay, what was the stack cookie then and all of that. And so this is something that we worked on and are built into our SoCs like a true hardware random number generators, and made changes to the kernel so that even straight at boot, it has access to good source of entropy and then actually uses that. The code snippet kind of identifies the issue. If you just look at get random in the kernel, then what it basically does is you make a call to the architecture specific, give me a random number, and if there's no such thing, then it falls back to, you can see like Chiffy's and the PID. That's the kind of stuff that will get you into trouble, long story short, right? And then so the change that we did in our case is that arch get random int actually does something as opposed to just doing nothing. Another thing is there are flags in the kernel that you would say that's existing feature, but so you could just turn it on, but the story is a little bit more complicated than that. DevMem and DevKmem are good examples of this. So if you compile in support for this, then you're going to have these nodes exposed from the kernel that basically give straight access to the entire memory. Of course, they are locked down to root access, so you would have to be the root user in user space. But still, in that case, because they're there, if you are a root user in user space, it's the equivalent of running inside a kernel. Which actually isn't supposed to be the case, and it's helpful for many scenarios if you can still make it harder to directly modify kernel contents, so directly read kernel contents even with that privilege level. So you could just say, hey, compile that out, and then there's no devmem, devkmem. The work that we had to do there is. Well, everybody knows about feature creep. So when some stuff is around for a while, then things will start to use it, right? And when it came to like removing devmem, it wasn't so easy as, oh, let's just turn this off because they broke stuff, because there were things that were actually using it. So it was some refactoring work to get to the point where nothing relies on it anymore, so we can actually remove it. And another thing I mentioned earlier, that there are upstream things that exist but actually don't exist for the ARM context. So that's one of the cases with proper WX or X separation. Point being, not having RWX pages in your memory. So that's something that you expect that your Linux kernel has, and it does, except for ARM, where it doesn't. It never had. And we wrote a patch for it so that for MSM kernels it exists. Here I want to also point out that now there's some development, some patches being submitted from Keyscook to actually make this work for upstream ARM as well. So hopefully soon enough it won't just be our kernels that have this, but like all the ARM space will have the benefit of that. But for the time being, that's not the case. And some other things that are, I guess, pretty simple, but you still got to do it. Like, that's, again, patches from Keyscook that existed for upstream and you had to pull in, like removing the parsing of %n altogether as a format string specifier in the kernel. So you basically kill those kind of printf bugs for good. And yet another is the strength of your stack protection and the strength of your stack cookies. So the thing with this is that if you're not familiar, then in the typical case, the typical way the stack protection gets used is that the compiler has some heuristics to decide which function to apply this to, which is an optimization feature. And the whole point is that the default options that exist in GCC are a little bit too optimal, I suppose. So there's going to be a lot of functions that would have benefited from a stack buffer overflow protection, but there's just no cookie compiled in there. And the Google team for Chrome OS, again, created a patch that they call Stack Protector Strong, that just tweaks the heuristic so that it covers a lot more functions that really should be covered. And that's, again, another thing that we pulled in and may work on our case as well. From the numbers alone, you kind of get an idea that this is a big difference. So with the default heuristic, you will cover something like 3% of your functions, and in the other case, 20%. And this was something that was very visible for us when we looked at the bugs we were finding, that there were a lot of cases where, oh, stack buffer overflow, oh, that shouldn't be so bad. Oh, wait, no. There's no stack cookie in this function again. And then no talk about Linux kernel security is complete without at least mentioning packs, especially in a Hungarian environment, because as we know, this, one of the authors of this is Pipac, who we are all very proud of. And so one thing that we did is looked at, how useful could this be, or what parts of this could we maybe pull in. And so to show you this graph, it kind of gives you an idea of the coverage of the various features. Without getting into the details of what each do, the point that you want to see is that from all the bugs that we have found, there's a large percentage of them that if you had packs, they would either be a lot harder to exploit, or they would be just straight up killed by the exploit mitigation. So that's awesome. Let's all quickly get packs. And then there's a bunch of challenges associated with this that I wanted to point out a little bit. Really, probably the biggest one that kind of destines this thing to be pushed off a little bit more into the future is that a really big feature of packs are a set of patches that essentially make sure that a kernel, when it's not supposed to, never touches user space. Whether you're talking about execution, so jumping straight back to user space. If you ever wrote a Linux kernel exploit, that's probably the first one that you wrote. Change the creds, go jump. When you get the jump, just go jump to some code that you wrote in user space, and then your user space code does the change your creds and stuff. But normally, you shouldn't be jumping back into executable code in user space in kernel context, obviously. So whether you're talking about execution or reads or writes, there's only a narrow scenarios where the kernel is supposed to be touching user space code when it's in kernel context, right? And so these patches from Spanner and the others, I suppose, add a lot of fortifying around this. The issue is that these things like kernexec and uderef rely on a feature of ARM that are called ARM domains. Again, the time really doesn't permit us to get into the details of this, but the long story short is that for various optimization reasons, for newer versions of ARM, so like after ARM 6+, this is a legacy now, so it's not used anymore. So basically, the implementation, even the sort of the ideas in it, you just couldn't use it. So you would have to do it in a different way. And then, so we are a little bit stuck in a moment where when you will be on 64-bit and when you will have LPAE, then you'll be able to do this the way you would really want to for Linux. But you're not really there yet in terms of the devices you have in your hand today. And then the way PAX does it, the domain stuff, that's already not supported. So there's a little bit of gap there that hopefully with time goes away. And there's another aspect of this whole thing that is worth talking about, which is that it's really hard when you want to get into the business of let's do something with PAX, because it's basically a gigantic monolithic patch. It's literally a single patch that covers a dozen different ideas. And there's no real documentation of these are the lines that would be this feature, these are the lines that would be that feature. And credit to Spanner, because they do it this way because in their head they support certain platforms. The ones they support, they provide a patch for. You can take it or leave it, which is a sane strategy from his perspective, I suppose, but makes it challenging if you want to derive work from it. So the story there is stay tuned, obviously. But I felt that if you're talking about this area, you gotta mention it and point out where is it that this area as a whole should be headed when you're talking about hardening the Android kernel security. And then for the last part of the talk, which we are not doing great on time, I suppose, I want to talk about the discovery and the response part of the process. So I mentioned in the beginning that, okay, you don't have that many bugs, or maybe they are harder to exploit, but you're still going to have some. There's still going to be 0 days. And then how quickly you get around to fixing them is really the whole game, right? If you're not fast enough, and if the half-life, if you will, of bugs is too long, then really you don't achieve all that much. If you pay attention to the clothes, to the news, you see the challenges with this. So, I mean, how many of you have heard of Tower Root, right? Not so many, I suppose, but this was one of the more recent exploits that was ported for Android as well. It's an upstream Linux kernel issue, so that works on every Linux, I suppose. And you still had a long window where this worked on various devices, so which highlights the point that your patching cycle needs to be rapid as well. Otherwise, there's still going to be enough bugs that you don't really make a dent with all the previous stuff. So let me talk about some of the stuff that we did. The first part is getting to faster discovery. So that means even seeing what's going on. Skipping this part, let me just talk about something that we call Night's Watch, which is basically a tool that we developed in-house based on Google custom search that essentially patrols the internet for us and finds us stuff that we care about, like exploits or IP leaks, or just generally interesting things in adversarial research. And then what you end up is kind of like a Twitter, if you will, or Twitter-like feed that we can go. This is obviously in-house, so don't put it on the internet. That we have a dedicated team that takes run-robin duties of reading and voting on, does this matter, does it not matter? And then it helps us, find things. And in the past, it has multiple occasions found ODAs we didn't see anywhere else. I guess they were kind of lost in the sea of Twitter, I suppose. So we find this useful. To draw a parallel, Netflix sometime recently actually published a set of tools, which is basically the same idea, I suppose. So since that's open source, if you're into this kind of stuff, I would refer you to kind of look at what they did, and maybe if you need something else, if you can use that, and so on. And then maybe the technically more interesting part of it is how do you do reversing fast? And that's something that we more and more saw that was important, that kind of if we go back 4 years ago, we had like Sebastian Kramer finding the good fight himself, just putting up these original Android roots that everybody heard of, like Rage Against the Cage and whatnot. I mean, this is all Sebastian putting on his blog, like, hey, here's a bug, and here's how I exploited it. And so that didn't need too much reverse engineering. It just needed the basic ability to read English, right? But we have moved far beyond that now. So the roots that come out, if you've heard about things like Sunshine, are really heavily obfuscated stuff. So you kind of need some good tools to get around to finding out, okay, what's the bug inside this? So just on a level of mention, a couple of things that we did. There's an IDA module that we call disarm. I think it's a cool name. Nico came up with that. I should give credit. Obviously, that should be clear, and I mentioned a lot of this is a team effort, and in particular, Nico Golde and Toro Ristov, we kind of prepared this presentation, the three of us together. So credit goes to them as well. So this is an IDA module that basically lets you do what everybody wants to do easily and quickly and with no hustle, which is just patching the control flow. And if you're familiar with IDA, you will know that it has a feature for like you can patch code, so it lets you change memory, but it doesn't have any more intelligence on top of that. So when you want to go like, okay, what I want to do is change so that that branch goes differently, then you can go and flip up your ARM reference and figure out, wait, which bits was that again? So what the module does is makes that quicker because it just turns into like, I don't want to go there, I want to go there. And then it does all the bit flipping underneath. And something that is probably more interesting and has done us a ton of service is a tool that we, unlike the previous one, have no imagination for the naming of it. So we just call it QPSI Trace. QPSI would be Qualcomm Product Security Initiative, so it's just the name of the team. And basically what this is it's a tool for instrumentation in the kernel to be able to track what all the syscalls are doing. If I refer back to the stuff that Jean-Bor was talking about with app level tracing of what apps are doing, imagine the same thing in the kernel, if you will. And then, oh, this slide is a little bit messed up, so I apologize for that. But it has all kinds of features, but instead of talking about the features, let me just kind of show you that here's a picture of what you do when you run your obfuscated exploit. Instead of, well, it just ran and something happened, you basically get a log that pinpoints you to, it made this ioctl to this syscall, which had this argument that is supposed to be user space, but it's kernel space, and this ended up flipping the UID. So you basically very quickly can dive down into, oh, probably this is like the 20 lines of the ioctl that I should look at. And as we have seen from the previous slide, once you're at those 20 lines, it becomes so much easier to figure out what your bug was. I see we are getting really at the end of the time, so apologies for running over. Let me just quickly wrap up. The last piece I wanted to talk about is what are the things we're doing on the actual vulnerability disclosure side to make it so that patching itself actually happens. The point I think I want to make here is this is our internal process that goes from, with some time commitments to do a root cause analysis that I was talking about, to develop a fix and propagate it to all the affected branches and all so on. I think the main thing you want to see here is right now, the last box on this is a CAF advisory. Code Aurora Forum, like I mentioned, is where we put up our code and where we also put up the public security advisories with the CVEs for all these bugs that are found. And I think if you leave it some thought, what you want to think about in your head is, it's good that there are less shallow bugs. It's good that they are harder to exploit. It's good that somebody's looking at this, but I want to have those fixes on my phone. So imagine that last box here, which goes CAF advisory. My phone is actually fetched, which is where there's further challenges, obviously, that remain. And like I said, that involves a lot of people, device manufacturers and network operators and so on. So I think that's a big area where this ecosystem as a whole needs to improve, particularly in the Android space. And hopefully we see more of that in the future. And just as wrapping up, let me just very quickly give you an idea for where you can reach us, where we put up our stuff. So here you just see the links. The slides will be published. So hopefully it helps you if you ever get to, hopefully you will, wanting to report an issue to us. We have your regular stuff, your product security website, where we put up the advisories, and there's a Hall of Fame and this kind of stuff. So really, if you just remember product-security@qualcomm.com, that's where you can contact us if you have stuff to report. So we're looking forward to that, and thank you so much for your attention. Obviously, we're already running over time, so I don't know if you can take questions right away, but maybe more in the speaker's corner. So I don't know, let me know. Any questions? No, okay, all right. Well then, thank you for your attention.